Hello and welcome to this series on Rust for Beginners. Rust is an exciting language for building performant and reliable programs for web, networking, embedded systems, and more. For years, Rust has been ranked as one of the most loved languages by developers. In this series, you will learn the fundamentals of Rust development. We'll start by downloading the tools you need to program with Rust and get started with writing our first app. Then we'll walk through and demo common concepts of the language and share what's unique about Rust, such as ownership and borrowing. Here's an overview of the full list of topics to expect. This series is for developers who are interested in and want to get started programming with Rust. While this is a beginner series for Rust, you should ideally already have some experience and familiarity with another programming language. You should also be comfortable using the command line to install programs and create directories. The goal is that by the end of this series, you will have enough knowledge to confidently go forth and write your own Rust programs. Now let's meet the instructors for this series. My name is Megan Lewis, and I'm a senior cloud advocate at Microsoft. I focus on emerging technologies, and this is just one of the topics that I've spent time diving into and using myself. In my day-to-day, you can find me creating and delivering learning experiences for audiences worldwide. I have worked professionally in tech for a decade and have producing learning content for half that time. I have a passion for teaching, and I am always keen to learn new and interesting things. I live in the San Francisco area with my husband and our 2 dogs.
My name is Nell Shamrell-Harrington, and I'm a principal software engineer here at Microsoft. I am also a member of the board of directors for the Rust Foundation. Along with working on Rust, I also work on a product called Clearly Defined, which tracks open source licenses. I have been working as a software engineer for over 10 years now. First, my focus was on Ruby, then on Rust, and now a combination of Rust and JavaScript. I live in Seattle, Washington with my wife, and we are the very proud parents of 3 adorable bunnies.
Hello, I'm Ryan Levick, and I'm a cloud developer advocate here at Microsoft based in Berlin, Germany, where I focus full-time on the Rust programming language. I've been in the software industry for nearly a decade, and I've been writing Rust since 2015. When I'm not teaching Rust to learners inside and outside of Microsoft, I'm actively participating in the Rust project and various initiatives, including performance, async programming, and more. Perhaps you've heard about Rust from colleagues or friends as an interesting new programming language that you should check out. But what kind of programming language is Rust? What makes it different from other programming languages? First, Rust is often described as a systems programming language. But what does this mean? Rust is a language used to build the software that powers the underlying systems that other software runs on top of. This typically means things like operating systems, web browsers, databases, low-latency web servers, firmware, small embedded devices, and other such low-level programs. Such programs have traditionally been written in languages like C and C++. This is because these programs require a high level of control over machine resources that other languages like JavaScript, Python, and even C# or Go don't typically allow for. Rust has many characteristics similar to C and C++ that allow users of the language this high level of control. But the biggest and most apparent of these is that, like C and C++, and unlike almost all other languages, Rust does not require the use of garbage collection. So if C and C++ already give programmers the control they need when writing such low-level programs, what does Rust bring that's new? Unlike C and C++, which do not guarantee that memory is used properly, Rust, by default, guarantees 100% memory safety. This means hard-to-debug issues that occur in C and C++, like use after free and dangling pointers, are simply not possible in Rust. As a side effect of Rust memory safety guarantees, whole other classes of bugs that you would find in C and C++, and even in other languages like C# and Java, are completely eliminated. These include null pointer exceptions, data races, iterator invalidation, and more. At the core of these guarantees is Rust's commitment to zero-cost abstractions, meaning that Rust generally checks at compile time before your program ever runs that these guarantees are upheld. Checking at compile time means we don't pay for these guarantees with runtime performance, as is the case when using garbage collection. Rust also provides a rich set of tools for creating these zero-cost abstractions, meaning that Rust is often extremely productive, expressive, and fun to read and write. Rust is a modern programming language, and so it comes equipped with tools you'd expect from a modern language, like integrated build tooling, a package manager, an open source repository of packages, a default testing framework, auto-generated documentation, and more. Being a productive language, Rust often attracts both programmers who have and have not worked with systems programming languages before. In addition to systems programming, Rust is also used as a productive high-level language for other things like web APIs, tools and utilities, gaming, desktop and mobile apps, and more. Rust's promise of productivity and memory safety requires a bit of upfront investment when learning the language in order to become familiar with some of its novel concepts. But once you've learned to think like a Rustation, we're sure that Rust will become an integral part of your programming toolbox.
This video covers one of the absolute best parts of the Rust language, the incredible Rustation community. We are a community where personal maturity and empathy are as important as technical excellence. You can find lots of information about the community at rustlang.org/community. This page features a list of the places Rustations gather and talk about Rust. These include the Rust Users Forum, which is a wonderful place to have asynchronous conversations about the experience of using Rust. And the Rust Internals Forum. The Internals Forum is where we discuss the development of Rust itself and the Rust ecosystem. You can also chat synchronously with other Rustations through the Rust Discord server, as well as through the Rust Lang Zulip organization. During normal times, the Rust community gets together physically at a few different events held throughout the year, including RustConf. Currently, due to the COVID-19 pandemic, we are holding events virtually. Most meetups are also being held virtually. That means that no matter where you are in the world, you can attend Rust meetups all over the globe. To see a list of Rust meetups meeting soon, make sure to subscribe to the This Week in Rust newsletter to keep up with what the Rust community is up to week. This newsletter is also a great place to find Rust open source projects that are looking for new contributors, as well as Rust jobs. Rust, both the project and the community, are governed through an RFC or request for comments process. For more information about this process, as well as how the Rust project is structured into teams, working groups, and project groups, make sure to check out the governance page of the official Rust language website. You can also participate in Rust discussions on social media, including with the RustLang hashtag on Twitter, as well as the Rust subreddit on Reddit. As you explore the Rust community, I encourage you to be unafraid to ask questions. We were all Rust newbies at one point, and we are committed to teaching each other, helping each other, and lifting each other up. I hope to see you in the Rust community soon.
In this video, I'll detail the steps that you need to follow to set up your development environment in order to begin writing Rust code. I'll be demonstrating how to install Rust and Visual Studio Code. The recommended way to install Rust is to use RustUp, the Rust toolchain installer. You can either find instructions at the rust-lang.org or head over to the rustup.rs website to find the installation instructions for your operating system. When I visit rustup.rs, I see a curl command to run in my terminal here. I am shown the option for a Unix operating system, which I am currently using. Windows subsystem for Linux users can also use this curl command. And if you are running Windows, you will see a different option prompting you to download and run the rustup-init.exe. Note that for a Windows user, you'll see another option here. You won't see this curl command. If I expand and say display all supported operating systems, I will see options for Windows here. But again, this should be different for you if you are using Windows. Note that for Windows users, you might also need to install the Visual Studio C++ build tools when prompted. For more information on this, you can visit rust-lang.org to find out how to install the Visual Studio C++ build tools. Heading back over to rustup.rs, I I will press the clipboard icon to copy the curl command, and then head over to the terminal and paste this command and install Rust Up Now. Once at the terminal, I'll paste the command and follow the on-screen instructions to complete the installation of Rust. This will take a few minutes. During installation, RustUp will try to configure the path environment variable at home/cargo/bin where all Rust tools are installed. Once installation is complete, I will see this command, Rust is installed now, great. I also see a command saying to get started, you need cargo's bin directory at home/.cargo/.bin in your path. This will be done automatically, but I might need to close and reopen my terminal for that to apply. To confirm it was installed correctly, I can type Rust Up in my terminal and see what output is presented to me. I notice that I have the version of Rust Up here, as well as different usage commands for how to use Rust Up. Additionally, you can confirm and see which version of Rust you have installed by typing rust c --version. And this will print out the version of Rust along with a commit hash and the date. Note that Rust has a 6-week rapid release process and supports a great number of platforms, so there are many builds of Rust available at any time. RustUp conveniently manages these builds in a consistent way on every platform that Rust supports. If you've installed RustUp in the past, you can update to the latest stable version of Rust by running the command rustup update. If you can't remember that, that's okay. You can head over to your terminal and type rustup to be presented with the list of usage commands and help you walk through the update process. Now that we have Rust, let's get set up with Visual Studio Code to write and run Rust programs. Visual Studio Code is not the only option to write and run code, but it is the most recommended as it's free and available on all operating systems. It also has great features to make it easy to navigate and organize your projects. To get started, let's visit the Visual Studio Code download page in the browser at code.visualstudio.com/download. The web page displays logos for Windows, Linux, and Mac. Select the version that corresponds to your operating system. So for me, I'll go ahead and select Mac. I get this notice, thanks for downloading VS Code for Mac, and I also notice that the download has started down below. With each operating system, you will generally follow the same steps to download and run the installer. Follow the prompts to install Visual Studio Code, and once the installation is complete, start up the Visual Studio Code application. And with that, your development environment is set up and ready to go. Now we are ready to write our first program. Now that your development environment is set up and ready to go, it's time to write your first program with Rust. We're going to create a Hello World program to get you familiar with how to create and run programs using the Rust compiler. To begin, go to your terminal or command prompt and create a new directory for this project. I personally like to keep all my projects in a projects directory. And then from there, I'm going to take it a step further to create another directory to store all of my Rust projects that I'll work on for the series of this course. To do that, I will type make dir rust_projects. And then I will cd to rust_projects. Once inside of this Rust projects directory, I will make another directory called hello_world. And then I will change directories to the Hello World directory. And then from there, what I want to do is open up this directory in Visual Studio Code so I can start writing this Hello World program. To do that, I can type code space dot, and that will be the shortcut to open up Visual Studio Code from my terminal. If that doesn't work for you, you'll need to make sure Visual Studio Code is added to your path. If you're on Windows, this will have been done automatically during installation. But if you're on a Mac like me, you might have to do this manually. You can add a shell command to install code in your path directly from Visual Studio Code. Let me demonstrate how to do that now. So once in Visual Studio Code, I will use the command palette. To do that, I can type Command-Shift-P to open the command palette and type shell command. And I'll see this result pop up to install code command and path. So I can go ahead and select that. After this, the terminal will need to be restarted for these changes to take effect. Focusing our attention on VS Code now, I will select to create a new file named main.rs. To do that, I will hover over the project name and select this icon to create a new file. And I will title this main.rs, rs being the extension for Rust programs. I'm going to start out by creating a function called main. Inside of these curly braces, what I will do will write out the message hello world to the terminal. To do that, I will use a macro called println, and that macro looks like this. Println followed by the exclamation, and then I can put the message inside surrounded by quotes. Hello, comma, world, exclamation. And then I'm going to go ahead and close that line with a semicolon. Now I have a very simple hello world program. I need to go ahead and save that. To do that, I will type Command S. Now what I want to do is compile and run the program. I'm going to use the terminal that's built into VS Code. To open up that terminal, I can go up to the top menu and select Terminal, New Terminal, or also use the shortcut, which for me is Control-tilde. Once there, what I want to do is first just confirm that I'm in the directory I expect. Now what I want to do is type rustc space main.rs, and this rustc command is going to go ahead and compile my project and produce a binary executable file in the same way C or C++ would do. So now if I were to type ls, I would see that in addition to main rs, I also have this main program here. If you were on Windows, you would see a main.exe executable file. So now I can go ahead and run this program, this binary executable, /main. And on Windows, it would be slightly different, where again, you would be running the main.exe. So once I enter here, I can see the output in my terminal says hello world. And with that, you have completed writing, compiling, and running your first program. Congratulations.
Previously, we've used Rust compiler rustc to compile Rust code into a native binary that we could run on our machine. Rust developers, however, rarely invoke the compiler directly. Instead, they use a tool called Cargo. Cargo is Rust's build tool, dependency manager, test runner, and project bootstrapper all rolled into one. So even though you can use Rust from a third-party build tool like Make, this is almost never necessary. Cargo offers an easy and intuitive way of building and running all of your Rust projects. Let's take a look at how to use it. If you've installed Rust through RustUp, you should already have Cargo installed on your machine. We'll use Cargo to create a new project for us using Cargo New. We'll call the project Cargo Hello World. Cargo has created everything we need for a new project. First, there's a cargo.toml file, which, as we'll soon see, is a simple manifest file describing metadata about our project, including its name, version, dependencies, and more. Next, there's a source directory with a single file, main.rs. This is where our Rust code lives. Cargo has also initialized the directory as a Git repository. Cargo has been friendly enough to pre-populate our main.rs file with some Hello World boilerplate. Rust makes it easy to write Hello World. We don't even have to write the code ourselves. To build this project, we can run cargo build. This builds a debug version of our binary and puts it in a newly created target directory in the debug subdirectory. We can run our binary directly as before. Cargo provides a convenient shortcut for building and running our project by running cargo run. We can even run tests for our project with cargo test, although our Hello World project doesn't have any tests yet. Now that we know how to use Cargo directly, let's open up this project in Visual Studio Code. Before we get started writing code, I'm going to install the Rust Analyzer extension for VS Code. This augments VS Code with features specific to Rust, including IntelliSense and inline compiler error annotations, so we know when we've typed something wrong. Rust Analyzer is the best tool for using Rust in VS Code, and it will soon replace the older Rust extension, which we won't need. When Rust Analyzer prompts us to do so, we'll need to hit the Install button to download and install the separate Rust Analyzer binary that powers the extension. Now that Rust Analyzer is installed, we can get started writing Rust.
In this video, let's focus on variables in Rust. Variables are important in any programming language as they are used in virtually every single program that you write. Variables can represent integers, strings, characters, booleans, and any other data type available in Rust. Variables are bound to values using the keyword let. So if I declare a new variable, I can type let x is equal to 5. Note that I use the let keyword, give the variable a name, x, and assign it a value, 5. By default, variable bindings are immutable. Immutable means that after a value is bound to a name, the value cannot be changed. So if I declare a variable let x is equal to 5, I cannot then later try to change the value of x with the statement x is equal to 6. This results in a compiler error. To be able to change the value of the variable, I would need to make the variable mutable by adding the mut keyword, MUT, before the variable name. So a mutable variable will be defined as let mut x is equal to 5, and then x can be bound to another value with the statement x equals to 6. Immutability creates predictability in our code. This means that we don't have to keep track of how and where a value will change. In some cases, you'll want to make variables mutable because the code will be more convenient to write, especially if you expect to reuse the same variable with changing values. Whatever route you choose, there are trade-offs to consider. If you have large data structures, mutating a variable may be faster than copying and returning new variables. With smaller data structures, creating new instances may be easier to work with. Immutable variables might remind you of another programming concept that is common in many programming languages. That concept is called constants. Just like with immutable variables, constants have a value that cannot change. They are always immutable and can't be used with the mut keyword. To declare constants, you use the const keyword along with the type of the value, the name, and the value itself. I know we haven't covered data types yet, so don't worry about the details of declaring types for now. An example of declaring a constant looks like this. Here I have a const named score limit with the type U32, which is an unsigned integer, 32-bit, and the value of that is 100. Note that the convention for constants is to use all capital letters with the name and have underscores in between the words. Constants can only be set to an expression, not the result of a function call or anything else with the value that is computed at program runtime. Constants are valid for the entire time a program runs within the scope they were declared in. The last concept I'm going to cover in this video is shadowing. You can also declare a new variable with the same name as the previous variable, which creates new binding. In Rust, this operation is called shadowing because the new variable shadows the previous variable. The old variable with the original value still exists, but you can't refer to it in this scope anymore. Let's say we have a variable let x is equal to 5. Then we can declare another variable named x with a different value. For example, let x is equal to x plus 1. What happens here is that the variable x binds to a value of 5. Then x is shadowed by taking the original value and adding 1 to it, so the value becomes 6. Shadowing allows the value to be updated again as many times as we use the let keyword again. Each time we do that, we are essentially creating a new variable. Now that I've explained the basics of variables and how they work, next I'll demonstrate examples of variables in action. Let's create a program to demonstrate how to declare and use variables. I'll start by making a new directory and project. I'll create this project inside of a Rust projects directory under my projects directory. At the directory location of your choosing, create a new project with cargo by running the command cargo new variables. When I run that command, I see that cargo created the binary application variables package. I will change directories to that new variables package now and open it in VS Code using the shortcut command code. Before I get started, note that I have the Rust Analyzer extension enabled. So when I'm typing, the extension will show helpful information, including errors and warnings. So we'll first focus our attention on the file source main.rs. I'm going to go ahead and delete this print line and start declaring a new variable. So I'm going to start it with just a variable called x is equal to 1 and put a semicolon at the end of that. And then let's use the println macro to print out the value of x. And I can do it just like that and add a semicolon at the end of the line. In the next line, I'll declare a variable named y, and I can say let y is equal to true. And notice that this is a Boolean type. And then I can print the value of y right after that. So I can say here the value of y is, and then include that value of y and close this with a semicolon. So to run the program, what I want to do now is to open up the terminal and Visual Studio Code. I can either go to Terminal, New Terminal, or I can use this shortcut here as described. So once I'm at my terminal, what I want to do is enter cargo run to go ahead and compile and run my program. And what I see printed out here is the value of x is 1 and the value of y is true. Now let's see what happens when we try to change the value of x. So after printing the value of x, I'll add in 2 lines. The first will be to assign x a new value, say x equals 2, and then the second will be to print the value of x again. So let's go ahead and just try on line 4 to say x is equal to 2, and then we want to be able to print the value of x again. So I'll just copy that line to line 5, and there we go. So now let's save this program and run it again. And I'll immediately notice that something is wrong here. So Rust Analyzer is telling me cannot assign twice to a mutable variable x. So assuming that I were to run the program, I would see the exact same error here. So whether you're using the Rust Analyzer or not, by the time that you actually compile the program, you will get that error. So if I wanted to be able to do this, I would need to go ahead and make sure that my variable x is mutable by adding that mute keyword. And after I add that mute keyword, I can go ahead and save this. I see the error goes away on line 4. So assuming now that when I run the program again, cargo run, I can see the value of x is 1, then the value of x changes to 2, and finally our value of y printed out. So that's just a reminder about mutable variables and needing to make sure to include that mute keyword if you want to change the value of a variable after it's bound. All right, so next I want to show an example of shadowing a variable. So after this println macro line on 8, what I want to do is shadow the value of y. So I can say let y is equal to false. So now I'm setting my Boolean value of y to false. So if I were to print the value of y again, we can assume that it will now become false. So let's go ahead and run this program again with cargo run. So I can compile my latest changes and run. And I see now the last line printed out here is that the value of y does become false. So finally, what I want to do is define a constant of type string. So what I'll do is just skip a line down here. And on line 12, I'll start by defining a new constant with the keyword const. And the name of the const will be string. And what I want to do here is make this type string. And it's going to be equal to the value hello. And I'll add a semicolon at the end of that. So now I've just defined a new constant called string with a string value and assigned to the value of hello. And I do get a warning from Rust Analyzer that the constant string is never used, so I need to go ahead and print that out. So on line 13, I will add a new print statement and say the value of the string constant is, and then we want to pass in that string constant and end with a semicolon. So now let's go ahead and run the program with cargo run. And what we'll see here is one more print statement where the value of the string constant is hello. And I do notice I have a typo, so let me go ahead and fix that and save the program again. That is what I wanted to show here. Of course, you'll continue to get more practice with variables and using variables in different ways throughout this series and as you write your own programs. Now that we've explored more about how variables work in this demo, let's move on to explore data types. In this video, I'll get into data types, specifically scalar types. A scalar type represents a single value and include integers, floating point numbers, booleans, and characters. If you're familiar with other programming languages, you'll recognize these data types. Let's explore how they work in Rust. First up, let's dig into integers. Integers are whole numbers, and they can either be signed or unsigned. Signed indicates that a number has a plus or a minus sign, so it can either be positive or negative. Unsigned numbers have no sign and are always positive. This table shows the following integer types that exist in Rust. There are various lengths for each signed and unsigned variable. Each signed variant can store numbers from 2 to the n minus 1 to 2 to the n minus 1 minus 1. So if I have an I8, so a signed 8-bit integer, then that can go from a range of 128 to 127. Unsigned variants can store numbers from 0 to 2 to the n minus 1. So an unsigned 8-bit integer can store numbers from 0 to 255. Additionally, the I size and U size type depends on the kind of computer your program is running on. 64 bits if you're running on 64-bit architecture, and 32 bits if you're using 32-bit architecture. The primary situation in which you use I size or U size is when indexing some sort of collection. Rust is a statically typed language, which means the compiler must know exactly the data type for each variable in your code. In most cases, the compiler can infer the type of some value, and you don't need to tell it explicitly in your code. If you're unsure of which integer type to use, Rust defaults to the I32 type, which is generally the fastest. Floating point numbers are simply numbers with decimal points. Rust floating point types are F32 and F64, which are 32 bits and 64 bits in size, respectively. The default type is F64 because on modern CPUs, it's roughly the same speed as F32, but capable of double the precision. All Rust number types support mathematical operations such as addition, subtraction, multiplication, division, and remainder. The Boolean type has either a value of true or false. The Boolean type is specified using the keyword bool, and Booleans are 1 byte in size. They are most used through conditional and control flow statements, which will be covered in another video. The character type is used to represent letters. A character type is specified using the char keyword, and character literals are specified with single quotes as opposed to string literals, which use double quotes. Character types are 4 bytes in size and represent a Unicode scalar value, which can include a single letter, accented letters, emojis, and more. That's the most important detail to cover about scalar types for now. Next, I'll jump into a demo. In this video, I'll demonstrate using scalar data types in action. To begin, I'll open up my terminal and create a new cargo project for scalars. I will start at my Rust projects directory, and once I'm there, I will type cargo new scalars and go ahead and create this new scalars package. And I will CD to move into the scalars directory. And once there, I will use the shortcut to open up Visual Studio Code. So with Visual Studio Code open, I'll go ahead under source and main.rs and focus my attention there. So I'll go ahead and close this sidebar so we can just focus on the full program view. And what we're going to start to do is just explore different examples of creating scalar data types. So let's go ahead and start with integers. I'll go ahead and just remove the print statement and replace that with a new variable called a, which I will say this is equal to 5. And just a reminder, this is going to be an I32 data type. I can also see that annotated here with Rust Analyzer. Going forward, I just won't do any comments to add that, but just helpful, especially to know if you want to add any comments after a line, just to provide a little bit more information for yourself or for any of the readers of the program. So next, let me define another variable called b, and I will say that b is, let's say that this is specifically going to be an unsigned 8-bit integer and equal to 1. So next, let's look at floating point numbers. I'm going to go ahead and declare a couple different variables for floating point numbers. So first, let's have let x is going to be equal to the value of 2.0. And I see that by default, this is the F64 type. Next, I'm going to have a value y and give y the explicit type of F32 is equal to 3.0. And add a semicolon at the end. Next, I want to start to use some of these variables that we've declared and do different mathematical operations. So I'm going to have let sum is equal to, let's add up a and B, and put a semicolon at the end of that. Notice that sum becomes type U8, so it just goes ahead and chooses a type. Then I want to have let difference, and what I can do here is let's look at our floating point numbers. How about we take x minus 1.0 and add a semicolon at the end of that line. I see that this is the float64 type still. Next, let's look at product, and let's take our variable a into account. So we can say something like 4 times a and get that value there, which would be 20. We can then look at, let's say, the quotient and how to divide different scalar types that we have. So let's now look at our floating point numbers again. We can take 9.0 perhaps divided by y. That would give us a nice, I'm just going to go ahead and say 9.0 divided by y, which will result in 3.0. And next, let's just look at the last kind of most common operation used, which would be the remainder. So I can say let remainder is equal to a modulo b. So we can take the remainder of a into b. So that's just giving you an idea of how we can use these different mathematical operations with different variables and data types that we've already defined. And what I'd like to look at next is how to define some Boolean types. So let's go ahead and just define a couple variables. Let t is equal to true. So again, the Rust compiler just automatically picks up that this is a Boolean type. I can also say let f and use that bool keyword there and set this f variable to false. And then finally, I just wanted to look at a couple examples of characters. Let's go ahead and first look at the example of using an emoji character. So I can say let c is equal to, I'm going to put the single quote in here. You notice that Rust Analyzer already picked up that this was a car because of that. And I just had this emoji copied into my clipboard, so I can come and paste that here. And then finally, I can say let d colon, specify that this is actually a character type, is equal to a. And I'm going to hold my a to bring up that little toolbar and press 1 so we can use some kind of accented letter. And so those are just a couple examples of characters. So I'm going to go ahead and save this program for now. You see it's a little bit messy. There's a lot going on here. I have some warnings, but let's just go ahead and run this for now in the terminal and see what happens. So I'm going to open my terminal and I'm going to say cargo run. And I see that my program compiles, and then I do get a number of warnings. The compiler is telling me if this is intentional, if it's not meant to be used, because this is an unused variable warning, then I can prefix it with an underscore. If I do want to use the variable, I could also add a print statement. So if you like, fix up the warnings as an extra challenge. You can also continue to use the Scalars project to explore how to use scalar data types in your programs.
Now that we've learned about simple scalar types, let's see how we group these together into compound data types composed of other data types. Let's start with arrays. Arrays are continuous groups of items. They have a fixed length, meaning they cannot grow as our program runs. And additionally, we must know this length at compile time. Finally, arrays are also heterogeneous, meaning that they can only contain items of the same data type. Declaring arrays is simple. They begin and end with opening and closing braces, and contain a comma-separated list of items. If you need to provide an explicit type, array types are written as an opening and closing brace around the type of the array's items, a semicolon, and the length of the array. Of course, Rust usually can infer the type of the array for you. We can access items in our arrays using indexing notation. All indexes must be of numbers of type usize. Accessing an array with a number literal and an index that is known to be out of bounds of the array will produce a warning. If we try to access an item at an index not in our array, Rust will crash, known also as a panic. Now let's take a look at tuples. Tuples, like arrays, are linear groups of items. Just like arrays, tuples have a fixed size, known at compile time, and they cannot change sizes as the program runs. However, unlike arrays, tuples are homogeneous, meaning their items can be of different types. Creating tuples is similar to creating arrays, but instead of braces, parentheses are used. Declaring the types of tuples is also straightforward, albeit a bit verbose. The type is a set of open and closed parentheses, followed by a comma-separated list of each element in the tuple. even if all the elements are all of the same type. It's possible to create an empty tuple which contains no elements. This might not sound very useful since tuples can't change size as your program runs, but it actually comes in handy in many situations. Just know, for now, the empty tuple has a special name, unit. Getting items from a tuple is a bit different than from an array. Instead of indexing notation, we use a numbered dot notation. If we try to access an item at an index that is not present in the tuple, Rust will always give us a compiler error. This means we can't ever accidentally try to access an item not present in our tuple, but it also means we can't access tuples using indices stored in variables. Let's head over to VS Code for a quick demo of all this in action. In this video, we'll take a look at creating compound data types in Rust. We'll create a new cargo project, open it in VS Code, and remove the hello world statement cargo added for us. We'll start by creating a simple array of U32s. Notice that Rust has inferred the type of the array, and Rust Analyzer has added a helpful annotation for us. If Rust can't infer the type for some reason, we can always add it explicitly ourselves. Notice that the length of the array is part of its type. If we add another element, we'll get an error, which Rust Analyzer displays for us in our editor. We can access the first element of this array using index notation. If we try to access the array at an index where it's clear to the compiler the index is outside of the array, we'll get a warning saying exactly that. If we instead access the array with an index that the compiler doesn't know is outside of the array, the code compiles without warnings. When we run this code, though, we'll get a panic, which crashes our program. Let's see what happens when we try to put something of the wrong type in our array. We get a compiler error showing that arrays always have to have elements of the same type. If we want instead to create a continuous collection of items of differing types, we can use tuples. Rust always tries to infer the types here, but in this case, it's unsure what type of number the second item in our tuple is. Let's add the type of the tuple explicitly. We can do this by adding parentheses and listing the type of each item in the tuple. Accessing elements in the tuple is done with dot notation. This always means accessing an index that doesn't exist in a tuple is a compiler error. That's the basics of using compound data types in Rust. Like many other languages, Rust uses functions as the basis for code reuse. Functions allow you to write chunks of code that can be called from other parts of your code. Let's take a look at how to define functions. Functions start with the keyword fn, followed by the function name, a list of arguments together with their types, all surrounded by parentheses, an optional return type, and a function body. There's some important things to remember about type annotations in functions. The types of arguments are always required. If the function returns a value, a return type is required as well. And finally, if the function does not return a value, then the return type defaults to unit, also known as the empty tuple. While we can explicitly write unit as a return type, there's no need to. Let's fill in the function we had before with a function body. Here we'll uppercase the input string and add an exclamation mark to it. You'll notice that we don't need to explicitly return the output value from our function with the return keyword. While Rust does have a return keyword that can be used to return values from functions, by default, the last value in the function body is the one to be returned. Calling a function is very straightforward. Here we'll create a new function, printExcited, which uses our exclaim function in its body. Simply write the name of the function, followed by parentheses and an argument. You'll notice our printExcited function doesn't have a return type since it doesn't return any value. The last line of our function is a call to println, which does not return value. Now that we've seen the basics of defining and calling functions, let's jump to a demo and see it all in action. We've seen the basics of how to define and use functions. Let's put it to use. We'll create a new project using Cargo and open it up in VS Code, just like we've done before. Let's create a function that returns the very last character of a string. We'll call it lastchar. We start with the fn keyword, then the name of the function, then the arguments and their types, then the return type, and finally, the body of the function. With our function body empty, Rust will complain to us that the function says it returns a char, but is actually returning an empty tuple, aka unit. We'll need to fill in the function body. I'll quickly do that with some functionality on strings. There's no need to understand this code fully at this point. Just know it's using a way to access characters of a string and asking for the next one starting from the back of the string. And finally, calling unwrap, which will crash the program if the string was empty and there was no last character. Notice we're not using the return keyword in our function. The last line of our function body is used as the return value of the function. If we need to return a value before the last line of the function, we need to use the return keyword. Let's return the siren emoji character when the string is empty. You might notice we don't end the last line with a semicolon. If we do, Rust will complain and say that we're returning unit instead of a char. Effectively, the semicolon says to not return the value from the last line of code. Since nothing is being returned explicitly, unit is returned. Calling our function should be straightforward. We simply name it and provide any arguments in between open and closed parentheses. Rust is complaining here because string literals aren't actually of type S string, but are instead a different type. We'll need to turn our string literal into a S string type using the string : from function. Once we call it on our string literal, the compiler is happy as we're now passing the right type to our function. With that, we now have experience defining and calling functions.
A struct is a popular custom data type for grouping related values. In this video, I'll explain the different types of structs, how to use them, and the methods and functions to specify a struct's data. A struct is a type that's composed of other types. Like tuples, the pieces of a struct can be different types, but you can name each piece of data so it's clear what the values mean. Because each field is named, structs are more flexible than tuples. Structs in Rust come in 3 flavors. There are classic structs, tuple structs, and unit structs. Classic C structs are the most commonly used. Each field defined within them has a name and a type. Tuple structs are similar to classic structs, but their fields have no names. And unit structs have no fields. They are called unit-like because they behave similarly to the unit type. The unit type has exactly one value. It is used when there are no other meaningful values that can be returned. To define a struct, the keyword struct is used, followed by the name of the struct. The name should describe the object appropriately so that it relates to the data being grouped together. An example of a classic struct that you see here is to define a car object and then group the related attributes, which are make, model, and year. Notice that make and model are of type string, and year is an unsigned integer, that is 32 bits. And then to use the struct after we've defined it, we create an instance of the struct by supplying the key-value pairs, where keys are the names of the fields and values are the data that we store in those fields. So to instantiate the car struct, we could do the following. Inside of the main function, we'll go ahead and declare a new variable called car1 by saying let car1, and that is going to be equal to the car struct. So then inside of that, we can specify the attributes about the car like this. We define a specific make, which is a string with Ford as the value. We define a model, which is also a string with Mustang as the value. And then finally, we define a year. And going forward, I can create more instances of the struct in the same way by supplying a unique name and a new set of key value pairs. Next, we would be able to get specific values from a struct by using the dot notation. For example, if I wanted to know the year of car 1, I can say car1.year and receive the value of 1967 back. So that should give you a high-level overview of how structs are used. Next up, join me for a demo to see more examples of structs in action and get a better idea how to use them in your programs. Let's use Visual Studio Code to better learn about how structs work in action. I'll go over to my terminal and begin by creating a new project called Structs. And then I'll open that up in Visual Studio Code. Inside of the main.rs file, I'll start by creating a classic C-type struct. Outside of the main function, I'll define a new struct called person. And since this is a classic C-type struct, this struct will have named fields. So my person will have a name that has a string type. They will have age, which is going to be an unsigned 8-bit integer. And then lastly, they will have a field called likes_oranges, which is a Boolean type. Then inside of the main function, I'll get rid of this print line and create a new instance of the person struct. So to do that, I will define a new variable called letPerson is equal to person, and go ahead and give values to the named field. So for name, I can say that this is a string from Adam to go ahead and give the person a name. And then I can say whether or not they like oranges, which is going to be equal to true. And then finally their age, which is going to be equal to 25. And then I can go ahead and close that with the curly brace and the semicolon at the end. So notice that in this instance, I can put the fields out of order. So likes oranges can come before age. It doesn't have to be in the same order that was defined in the struct definition. If I want to access a value in person, I can use the dot notation like this. So I'll go ahead and add a print line to say person name is, and then what I want to do is go ahead and say person and use the dot notation dot name to specify that I want the value of their name. So now with this program as is, let me open up the terminal and run it. I can do that with the command cargo run, and I'll wait for a second to see my program compile and run. And I see that there are a couple warnings, and that's okay because those are just some unused fields. And then I do see that the person's name is Adam printed out there. In the next example, I'll focus on creating a tuple-typed struct. This struct is going to be called point2d. So I can define that now right after the person struct. And it's going to take two fields that do not specify a name and only a type. The types are going to be unsigned 32-bit integers. And I can define it just like that and put a semicolon at the end. For this struct, I'm only going to be defining x and y coordinates. I really only care about the value, so I don't need to name the fields. Inside of the main function, I want to create an instance of the point2d struct and assign that to a variable called origin. So the way that will look is after this print line, I'll go ahead and skip a line and say let origin is equal to point2d, and I want to provide an x and y coordinate here. So my x will be 100 and my y will be 200. I can go ahead and add a semicolon at the end of that line. Tuple struct instances behave like tuples. For example, you can use the dot notation with an index to access an individual value. I'll show an example of that now. On the next line, I can go ahead and print out a couple values where I'll use the dot notation with an index. So to do that, I will say point contains, and I'll use this colon question mark notation to indicate that it will be for my x value, and the same notation here to say this is going to be for my y value. And then after that, I want to specify that I want origin at index 0, and I also want my origin at index 1. So then this will go ahead and print out 100 and 200 as the values when I run this program. You can also destructure these tuple struct instances into individual pieces. Say I have let point2d x, y is equal to origin. So here what I'm doing is the exact opposite of this line on line 18, where I'm kind of defining a new variable, a new instance here. Let point2d x, y is equal to origin. Then I can skip a line and add a new print statement to say point contains, and I'm going to use that same notation from before, the colon with the question mark for my x, and the colon with the question mark to indicate that's where I want to have a placeholder for my y. And then I'll add a comma and use x and y there. So this is just a classic example of destructuring my tuple struct. So I'll go ahead and run this example now with cargo run. And here is what we have printed out. So the first print line, of course, is Adam. We saw that previously. The second one, his point contains 100 and 200 by using the index of that struct. And then we're doing a destruct example where we're taking the indexes here, and that is going to print out the same thing. Point contains 100 and 200. This video provided examples of how to create and instantiate structs. You should now feel more comfortable about how to use classic and tuple type structs in your programs. Enums are a custom type that list all the possible variants or enumerations of some data. In this video, we'll explore how to define and use enums. Enums are a common feature across programming languages, but their capabilities may differ from language to language. And you'll see how they work in Rust. Enums in Rust are commonly referred to as algebraic data types, which are types formed by combining other types. This data type is common in functional languages such as F# and Haskell. Let's explore an example of what an enum can contain to give you a better idea of how to use them. Say that we want to list all variations of cardinal directions. Our enum would be called cardinal directions and can be defined using the keyword enum before the name. And in the enum, the variations would be north, south, east, and west. Now, cardinal directions is a custom data type that we can use in our code. Instances of the variants can be created like this. Let north is equal to the cardinal directions, : north. Let south is equal to cardinal directions, : south, and so on. The variants of the enum are namespaced under its identifier, and a double colon separates them. Notice that in the original definition, the variants didn't include a type. That means that to associate a type, we would need to use something like a struct, for example. Or we could also define the enum differently to specify a type for each variant. So in this example here, you see that after the name of the variant, inside of parentheses, a type is defined. The type is the same for each one of the variants here, which is string. And then down in the main function, I can define a variable called west to access that west variant directly from the enum. So here what I'm doing is attaching a data type to each variant of the enum directly. So there's no need for any kind of extra step to be done, like a struct to define the type. The cool thing about enums is that you can put any kind of data inside a variant: strings, numeric types, structs, or even other enums. An enum can have a variety of types as well. So there's flexibility on the type of data and variants that are in an enum. Enums are like structs, but have more advantages. First, they only describe what kind of data will be stored, not the actual data. Additionally, each variant in an enum can have different types and amounts of associated data, and structs don't have as much flexibility there. And lastly, an enum stores all variants under the same type. So in our example, all variants are stored under the cardinal directions type. So there's the overview of what enums are and how to define and use them. Hopefully this video helped your understanding of how enums differ from structs. Next up, let's look at some more examples of enums in action. In this video, let's use Visual Studio Code to write a couple different enum definitions. I'll start by creating a new project called Enums over in my terminal now. Once at my terminal in the Rust projects directory, I'm going to type cargo new enums. And then once that enums package is created, I will change directories to enums and open that up in Visual Studio Code. Once I'm in Visual Studio Code, I'll focus my attention on the main.rs program. And above the main function, I'll start by defining an enum to classify a web event. This enum will be called web event and have multiple different variants. First, there's going to be page load and page unload. Notice that these variants have no data associated with them at all. These are unit-like. Next, I will have a key press variant, which takes in a single character. This is like a tuple struct. Next up, I'll have paste, which will allow a string value. And then finally, I'll have a click variant, which will include an anonymous struct, including the types X, I64, and Y, I64. In this example, you can get a better picture for how flexible enums truly are, with being able to group lots of different types of data together. When I want to use or access a variant from the web event enum, I can do the following. Inside of the main function, I'll get rid of the println line and go ahead and define a new variable that I'll call quit. And then I will call the web event with the key press variant. And for the character, I want to pass in Q to indicate that that will quit the program. That's a simple way of how I can define one variable to access a variant. A similar convention can be followed when setting the value of other variants to variables. Another type of enum to explore is the option enum. This enum is defined by the standard library. The option type is used in many places because it captures the scenarios in which a value can either be something or nothing. Rust doesn't have null values, but it does have an enum to encode the concept of a value being either null or not null. The option enum is defined by the standard library as follows. I use the enum keyword and specify the name of the enum, which is option, with a parameter of t, which is a generic trait, which we'll talk about later. Then for the variants of this enum, I will have some, which takes a type t, and then I will have none as the second variant there. What's interesting about the option enum is that it's included in the prelude, and it's not necessary to bring it into scope explicitly. So the variants some and none can be used directly without the option prefix. Again, the T syntax that you see here and in the some variant is a generic type parameter. What's important to know is that T means that it can hold some value that's one piece of data of any type. Let's explore how to use the option enum now. I can do the following if I want to access the some variant of the enum option. I can define a variable called something is equal to sum1. So this is how I can go ahead and use the sum variant of the option enum and just pass in some value, which here is type I32. Using the option enum is helpful to prevent common issues and handling that scenario before encountering an error. Not having to worry about incorrectly assuming a not null value helps you to be more confident in your code. There you saw a couple examples of enums in action. Enums are commonly used in programs, so it's important to get familiar with understanding how to implement and use them. An essential part of any program is to modify how code is run with control flow. In this video, we'll explore some solutions to use to implement control flow. We'll focus on if, else, and match expressions. If conditions are the most common ways to introduce control flow into branch code. The way they work is you provide a condition and then execute a block of code if the condition is met. A common example is a condition around a value. For example, if price is greater than 0, then we can print true as output. Notice that the expression starts with the keyword if and is followed by a condition which always evaluates the Boolean type with the value true or false. This if expression evaluates to true. Let's take a look at another example, adding in an else expression after the if. So here we're saying if price is greater than 0, then print out, condition is true, else print out, condition is false. An else expression can be added optionally to be explicit about the alternative block of code to execute. If no else is provided, the program will skip the if block if the condition is false and move on to continue executing the program. If you have more than 2 conditions to check, if and else can be combined in an else if expression. For example, if price is equal to 1, print the price is 1. Else if price is equal to 2, print the price is 2. Else print price other. In the case all if and else if conditions evaluate to false, then the else block is executed. Another option that is used regularly in programs to make decisions by comparison is the match expression. This is similar to a switch in other languages like C. And Rust is able to provide this pattern matching with the match keyword. Match has what's called a scrutiny expression, which is the value provided to compare to the patterns. And arms within the match expression are evaluated and compared with the scrutiny expression. Here is a simple example of a match expression where we have a value of x is equal to 1, match for x, and the values 1, 2, 3, 4, 5, and then something else at the end. So what's happening here is that the scrutiny expression is x with the value of 1 and is compared with each of the arms in the match expression. Each arm has two parts, a pattern and some code. The arrow operator separates the pattern and then the code to run. The code is executed for the first pattern that matches, just like with an if-else expression. The first arm with the matching pattern is chosen as the branch target of the match. If none of the other arms match, then the arm with the underscore will be chosen. The very first arm has a value of 1, so that will be chosen as the branch target, and the program will print out 1. Although the syntax and format of this expression is different, it is still somewhat similar to an if and else if expression, where multiple conditions are evaluated to determine how the code will execute next. The big difference is that while an if needs to return a Boolean type, match can return any type. So that's the overview of if, else, and match expressions. In the next video, let's see more demos of using these control flows in action. In this video, I'll explore if, else, and match control flow operators in more detail with demos. I'll begin by creating a new project called Control Flow. I'll do that in my terminal window now. Once at my Rust projects directory in the terminal window, I will type cargo new control underscore flow. Then once that package is created, I'll go ahead and change directories to the control flow package and open that up in Visual Studio Code. Once the project is open in Visual Studio Code, I'll focus my attention on the main.rs program. Inside of the main function, I'll go ahead and get rid of this print statement, and let's go ahead and start by writing a couple simple if-else expressions. The first, I will say if 1 is equal to 2, then I want to print math is broken. Else, I can go ahead and say print everything is fine. Cool. So in this example, the condition of if is the expression 1 is equal to 2, which evaluates into a Boolean type with the value false. Unlike in most languages, if blocks can also act as expressions. So remember that all branches must return the same type for our code to compile. So let's look at another example of that now. I'll define a variable called formal that is equal to true. And then I want to define another variable called grading, which is going to be equal to an if expression called if formal. And so if formal is equal to true, I want to go ahead and print out good evening. Else, if formal is equal to false, I want to go ahead and print out hey friend, and add a semicolon at the end of that, and also a semicolon at the end of this expression here. So in this example, we can see that the result of the if expression is stored in the greeting variable. And then from that, we're able to use this new if expression to evaluate what to print out as the greeting. You can handle multiple conditions by combining if and else in an else if expression. For example, let's say let number is equal to 6. And then if number modulo 4 is equal to 0, I want to go ahead and print out number is divisible by 4. Else if number modulo 3 is equal to 0, then I want to say print ln number is divisible by 3. And finally, I can say else print ln number is not divisible by 4 or 3 and add a semicolon at the end of that. And I can also fix my typo up here. Thanks VS Code for calling that out for me, is not divisible by 3. So here is just a simple example where we can have multiple branches and you can add as many branches as you want if you go ahead and add in that else if keyword. Let's go ahead and look at one more example where we can use match. To begin in this example, I want to define a variable called Boolean, which is going to be equal to true. And then I want to say let binary is equal to match Boolean, and then add some braces. So now I'm going to print out all of the possible values, which for a Boolean is really straightforward. I'm going to have either 0 or I'm going to have 1. And then there we have it. I can add a semicolon at the end of that. So now we define Boolean is equal to true. So when it comes down to evaluate the match statement, it's going to go through these two different arms here. So it's going to skip the first arm since that is equal to false, and then select true as the matching arm. So then the value printed out will be 1. So there's a few examples of using if, else, and match in action. Continue to explore on your own to get more familiar with these expressions. Control flow expressions like if and else are great when we are just executing a statement of code once. But what about when we want to execute some code more than once? In that case, loops come to the rescue. A loop prints through a block of code repeatedly until a condition is met or we tell it to stop executing. In Rust, there are 3 kinds of loops: loop, while, and for. Let's talk about each one. First up, I'll focus on a loop. The loop keyword in Rust is used to execute over a block of code forever until it is stopped or the program quits. Let's take a look at the most basic implementation of a loop. Here in the code example, you see inside the main function, we use the loop keyword, and then within braces, there's a print ln macro line that says I loop forever. Currently, this loop will just do that. It will run through and print this statement over and over. Instead of having this code run infinitely, the break keyword can be used. When the break keyword is encountered, the program will stop executing the loop and move on to the next line of code. Whenever you use a loop, you'll want to include a break keyword at some point to stop the loop. Loops are used in scenarios when you know an operation might fail and need to give it another try. Next, let's talk about while loops. While loops are referred to as conditional loops. While the condition they specify is true, the loop will run continuously. When the condition is met or becomes false, the program exits the loop, stops, and continues with the program. A simple while loop looks like this. Let a mutable number is equal to 3. While the number is not equal to 0, we're going to print out the number and then decrement the number by 1. We're going to go through this while loop until the number is equal to 0. And that's when we will break out of that loop and continue on to the next line, where we'll print out liftoff to the output window. What's awesome about while loops is that they eliminate the need for multiple if and else expressions, and they conditionally repeat as opposed to the loop. And lastly, there are for loops. For loops are best for iterating over elements in a collection, like an array. With each pass of the for loop, values are extracted from an iterator. In this code sample, inside of the main function, we define an array called A with 5 elements. The code iterates through each element in the array and binds it to the element variable. Then the value is printed. Once the end of the array is reached, the code will continue on executing. The same thing can be achieved with a while loop, but a for loop is much more concise. In addition, it eliminates the chance of bugs or errors from possibly going beyond the range of the elements in the array. For these reasons, for loops tend to be the most commonly used over while loops. In the next video, let's look at some more examples of loops. To explore loops further, we'll get some hands-on experience creating and running loops and Visual Studio Code in this video. Inside my terminal, once I'm in my Rust projects directory, I will type cargo new loops. Then let's go ahead and change directories to the loops package and open that up. So let's start with an example of a loop with a break. I'm going to define a mutable variable called I, which is going to be equal to 1. And then I want to define a new variable called something, which is going to be equal to this loop. And what we're going to do in this loop is constantly increment the value of I. So we're going to have I times 2 is going to be equal to I. And then I want to say if I is greater than 100, then I want to go ahead and break I. So it's going to break out of that loop when I is anything greater than 100. And then I'm going to go ahead and close out this loop, and then I can add an assertion. So an assertion here, I might just want to look at the value and what I expect the value to be after a certain time. So I'm going to use the assert equal macro and say that something will eventually be equal to 128. So what's happening in this loop, we can just take a closer look, is that I is going to be equal to 1. It's going to come into this loop. I times 2 is going to be equal to 2. So if I is less than 100, will we break out of this? No. So then we come around the loop again. So 2 times I is going to be equal to I, so that's going to be 4. And then we're going to continue through this loop until we have a value greater than 100. And at that point, the value is going to actually be equal to 128. So you can run that and assert that this actually is correct. Next, let's go ahead and explore a while loop. So here I want to have let mute counter is equal to 0. And then I can say while counter is less than 10. I want to print out the value hello. And then what I want to do is increment the value of my counter. So counter is going to be equal to counter plus 1. And so we're going to keep going through this loop with the counter starting at 0. Within the first while loop, the counter is going to be equal to 1. And then we're going to do this all the way until the value of counter is 9, which is less than 10. And the last time when it gets incremented, we will not be able to go through that loop again. So then the program can continue executing. And for our last demonstration, I want to show another example of a for loop. So let's go ahead and look at an example of creating an iterator with a for loop using the range notation. So for this, I want to say for each item in the range of 0 to 5. So I can annotate that just by using those 2 dots. And then I want to go ahead and add a print statement. And within this print statement, I want to go ahead and print out each item times 2. In this example, the code iterates through the numbers 0, 1, 2, 3, and 4 and binds them to the item variable. For each iteration, the value printed will be item times 2. So first, when the number is bound to the item variable for 0, it's going to be 0 times 2, which is equal to 0. Then for 1, it'll be 1 times 2, which is equal to 2, and so on until the upper range of 4 is reached. So I hope that these examples of seeing loop, while, and for help to build your understanding of how to use loops. There are still lots of different scenarios that we didn't cover here, so feel free to explore this program more, adding in your own examples, running, and just seeing what else you can learn about loops. Error handling is the process of anticipating and working with the possibility of failure. Learning how to manage errors effectively in Rust before they become a problem will be extremely helpful at saving you time and sanity. In this video, I'll describe the multiple ways to handle errors in Rust. We'll focus on using panic to deal with unrecoverable errors, option for possible non-existent values, and result for handling other things that might go wrong. Panicking is the simplest way to handle errors in Rust. You can use the panic macro to quit the program execution. Using a panic macro would look like this. Wherever we want inside of the main function, we can include the panic macro along with a message to print out when the program stops executing. So what happens when the panic macro executes? First, a failure message will be printed, then the program unwinds and cleans up the stack, and then it quits. Generally, a panic macro should only be used when a program comes to an unrecoverable state. Rust can also emit a panic on some operations, such as division by 0 or an attempt to access an index that isn't an array, a vector, or a hash map. Take, for example, this piece of code. Here we have a vector with items 0, 1, 2, and 3, and then we try to print out the value of v at index 6. This will cause a panic because there is no v of index 6. The maximum index that we have in this vector is 3. Many errors aren't so bad that the program needs to stop and panic. Maybe you encounter a recoverable error where you need to handle the absence of values. The option T enum, as introduced in the enum video, manages the possibility of a null or non-existent value. The option enum is defined as the following. We have an enum called option T with two variants, none and some. The T part of option T states that the type T is a generic and associated with the some variant. None indicates that no element was found, and some means that an element of type T was found. If the value exists at a specified index, it's wrapped in the option some value, where the value is type T. If the index is out of bounds, it will return an option none value instead. For other recoverable errors that are more common, the result type can be used. Examples of recoverable errors might be when a function fails or an operation that you expect to work doesn't. Maybe your program tries to open a file that doesn't yet exist. Luckily, Rust provides the result enum for returning and propagating errors. The result enum is defined as the following. We have an enum named result with type T and E. These are both generic types, and the variants that the result enum has are OK and T. So the OK T variant represents a success and contains a value. The error E variant represents an error. The result enum is principally used for input and output operations, such as parsing strings into other types, file access, and data validation. In contrast to the option type, which describes the possibility of the absence of a value, the result type is best suited whenever failures are expected. The result type also has the unwrap and expect helper methods. If the result value is the OK variant, the unwrap method will return the value inside OK. If the result is the error variant, unwrap will call the panic macro for us. The expect method is used in a similar way as unwrap, where it either returns a value or calls the panic macro. When it calls the panic macro, it allows us to also write a detailed error message. The last thing I want to call out is the question mark operator. This operator works similar to how match statements work, but eliminates the need for an entire statement and only a question mark is used. The question mark operator applies to a result value and unwraps the inner value if it was the OK variant. If the result is the error variant, it returns from the point of the function you're currently in. The question mark operator can also be used with the option enum, where a value will be returned for some variant of T, and none will be returned for the none variant. Instead of needing a match statement, only the question mark operator is needed. This makes code look cleaner and still allows us to handle errors nicely, passing them up the call stack. That is the overview of Rust error handling features. The various options for error handling exist to help you write more robust code. Becoming familiar with when and how to use these error types can make all the difference in ensuring your code is reliable and safe. In the next video, I'll explore more code examples using the various forms of error handling. Let's get some hands-on experience with error handling and Rust. I'll start by creating a new project called Errors in my terminal now. And then I'll open up this project in VS Code. I'll open up the main.rs file and start by looking at an example with the panic macro. Inside of the main function, I'm going to go ahead and get rid of this println line and use the panic macro. And inside of that, I will have the text farewell, and then go ahead and close that with a semicolon. I can run the program using cargo run, and then I'll see that the program panicked at line 2 with the message farewell. So now let's look at another example that doesn't explicitly throw a panic, but will ultimately result in an unrecoverable state. So what I want to do on line 2 is remove this panic statement. And I'm going to then specify a vector named v. And this vector is going to have the values 0, 1, 2, and 3. On the next line, I will use a print statement to go ahead and print out an index of the vector. Let's try to print out the index of 6. So let's go ahead and see what happens when we do this now. After After running this program, I see that the program panicked because of an index out of bounds. So panics can be thrown in programs when they reach an unrecoverable state, like you see here. Whether or not we use the panic keyword, sometimes panics will arise in your programs. Now let's look at an example where we use the option enum, where absence of a value is a possibility and can either return some or none as a value. So I am going to go ahead and comment these lines out here for now since they are throwing a panic. So what I'm going to do is define a new variable called fruits, and this is going to be a vector of different fruits. So let's go ahead and put some fruits in our vector. We're going to have a banana, an apple, and a coconut. And then I'm going to close that with a semicolon. So now what I want to do with this vector is to access fruits. I want to say let first is equal to fruit dot get 0. So I just want to go ahead and grab the item in that 0 index. And then I can say print ln. And I want to grab the first variable and print that out there. Then let's say that I have a variable called third, and I want to go ahead and get the third item in the fruits vector. So for this, I can say fruits dot get 2. And then similarly, I'll go ahead and print that out like this, and add a semicolon at the end. And then for one more example here, I want to try to access a vector's non-existent index. So let's go ahead and say let non_existent is equal to fruits dot get. And we can just throw any index that we want in here, but something that's obviously just not going to be existent in our vector. And then on the next line, I'll go ahead and print out that value. Let me go ahead and run this. So I see printed out some banana, some coconut, and then finally none. Since a value exists at a specified index, like it does with the first and the third items, it's going to print out the actual value. So it's using that option some value variant. If the index is out of bounds, like it is with the non-existent variable, it's going to access the option none value variant and return none. So this is a good example here of seeing this option enum in action. So I'm going to look at one more example of using the result enum. I will first go ahead and comment out this example here. Within the result enum, we'll return OK if there's a value or error if there's an error. Outside of the main function at the top of the file, I am going to import the standard library fs and use file. And then inside of the main function after the commented code, I want to define a new variable called left. F is going to be equal to file open, and then I'm going to put the name of the file within the quotes here. After that, I want to say let F is equal to match F, and then I'll use the result enum to try to unwrap the file contents. So I'm going to say OK file and then return the file if in fact there is a file found. Otherwise, this will result in an error, and then the program will panic. And I can say that we can't open the file, and let's print out that error after that. And then I'll go ahead and add a semicolon at the end of this. And let's try to run the program as is to go ahead and see the output now. After running the program, I see that thread main panicked, can't open the file, and the message is no such file or directory. I also know that this error is coming from line 22. So this is just one way of how you can use this match statement where I either return an OK or an error. Something else that I want to go ahead and do though is show examples for how we can use the unwrap and expect helper methods. I can go ahead and get rid of this match statement here, and let's go ahead and try to use the unwrap helper method just like that and see what happens now when we run the program. So this also results in a panic at line 18, since there is no such file or directory. This is much less code needed for essentially the same result output that we get here. Another way that we can handle the situation is to use the expect helper method. Instead of using unwrap, I can go ahead and call expect here. And what's different about expect than unwrap is that I can go ahead and add a message here to provide a little bit more context in case of a panic. panic. So I can say vel2 open hello.txt. And now let's go ahead and run the program again. And notice that this error is a little bit different. Here I have this message, failed to open hello text that I defined. I also then have no such file or directory. So really the convenient thing here is being able to specify an extra message that makes it a little bit more clear if this were to panic where it's happening in the program. So it can definitely save you some time debugging. When integrating error handling in your programs, consider which of these options makes the most sense for your use case. As you become more familiar with Rust, I recommend trying out multiple ways of error handling to decide what works best in different scenarios.
Ownership is one of the most unique and critical aspects of Rust to understand. This video will take you through concepts of memory management and how Rust can guarantee memory safety without requiring the use of a garbage collector. Ownership has to do with how your program manages memory. When you run a program in Rust, or in most other major programming languages, it stores data in two differently structured parts of your computer's memory. These structures are called the stack and the heap. The stack, as its name implies, is a stack data structure. The way data moves through it is last in, first out. Let's look at an illustration of how this works. Let's add data to this stack. And after we've added the data, if we wanted to take data off the stack, we would take that same piece of data we just added off of the stack. The stack is where Rust stores data with a known fixed size. If we were to declare a 32-bit integer in our program, and then set it to the value of 5, a 32-bit integer has a known fixed size at compile time. We know it will take up to 32 bits of space when we run the program. Because the size of the value is known at compile time, both the variable and the value of the variable would be stored on the stack. However, what about a data type that can change size at runtime? Let's consider a vector. Notice that this vector is mutable. That means this vector can change size while the program is running. We could add another value to the vector, and then print out the value of the vector, and when we run this code, we see these 4 values. Because the size of the vector can change, this time we store data in both the stack and the heap. On the stack, we store a representation of the vector variable itself and a pointer to a memory address on the heap. The heap is where we store the actual content of the vector. If we were to drop this vector using Rust drop method, both the data on the stack and the heap would no longer be accessible. So far, the concepts we've discussed are not unique to Rust. Most programming languages store data on both a stack and a heap. Where they differ is how they manage that memory, especially when values are dropped or go out of scope. Let's use a different data type this time. A string also stores data on both the stack and the heap. Notice that this string is mutable. That means it can change while the program is running. This means the string needs to be stored on both the stack and the heap. We could add content to the string like this, and then print the string. When we run this program, we see the full modified string value printed out. Now let's consider what would happen if we were to create a new string and assign it the value of our original string. In this case, we create a copy of the data stored on the stack. So we would take the representation of our original string on the stack, including the pointer to the heap, copy it, and assign it to the new string variable. This means our second string would have the same pointer as the first string. While we do copy what is stored on the stack, we do not copy what is stored on the heap. So the pointer associated with the second string would point to the exact same address as the pointer associated with the first string. This introduces a new question. What if we were to delete or drop the first string? It seems like both the data stored on the stack and the heap for the first variable would no longer be valid. Does that mean the second string would still point to the same place on the heap, even if the value on the heap is no longer valid? Rust has rules to prevent this situation. But before we go into them, let's briefly cover how other programming languages have handled this problem. This scenario, where you have a pointer on the stack pointing to data on the heap that is no longer valid, is known as a dangling pointer. This can cause your program to crash and can be a major security issue. Until Rust came along, there were two main approaches to preventing issues like this. Languages like C and C++ depend on the programmer to explicitly manage the memory used by their code. That means it is your responsibility to allocate or deallocate memory as your program needs it. This may sound straightforward in theory, but as code bases grow and become more complex, manually managing memory becomes much more difficult in practice. The other approach that some programming languages have taken is to use a garbage collector. If you have used a language like Python, Ruby, or JavaScript, you have used a garbage collected language. The garbage collector is a program that runs while your program runs. Its job is to constantly look for memory that is no longer used and clean up any references to that memory. This works well for many languages, but using a garbage collector adds overhead, which makes these languages less suitable for low-level systems programming. Rust takes a third approach to memory management called ownership. Ownership consists of a set of rules that the Rust compiler verifies at compile time. The first rule is each value in Rust has a variable that is called its owner. So if we were to look back at this line of code, the first variable is the owner of this string. Now let's add this line of code, which assigns the value of our second variable to be the value of our first variable. And this brings us to the second rule of ownership. There can only be one owner of a value at a time. Both these variables cannot be owners of the same value at the same time. We need to completely move ownership to the second variable, and then invalidate the first variable. If you are familiar with C++, this might sound like making a shallow copy, but there's a key difference. Rust doesn't just copy the data in the stack. It then invalidates the variable we moved the data from. Once the value that used to be associated with the first variable is moved to the second variable, the first variable is no longer considered valid by our Rust program. If we were to try to access the first variable after its value is moved, and then try to compile the code, we would receive an error. This rule means we don't need to worry about dangling pointers. Only one variable can be pointing to the data on the heap at any given time. This prevents a lot of memory safety issues, including dangling pointers, double free, which involves trying to free memory that has already been freed, and memory leaks, which involve not freeing memory that should have been freed. This is also helped by the third rule of ownership. When the owner goes out of scope, the value will be dropped. To understand this rule, let's go over what we mean by scope in the context of Rust. A variable's scope is the range within a program for which that variable and the value of the variable are valid. And we'll discuss that more in the next video. This gives you a high-level overview of ownership in Rust. In the next video, we will examine how these rules apply to values that are passed between functions. I'll see you there! Ownership and scopes are especially important to keep in mind when we are passing values between Rust functions. Let's consider this code, which creates the say variable in our main function, and the value of that variable is a string. And we have a second function which takes a string and prints it out. When I pass the value of the say variable to the second function, I transfer ownership of the value to that function. Once I transfer ownership, the variable is now out of scope in my main function. If I try to access the value of the say variable in my main function after it has been transferred, I receive an error. The compiler catches that I'm trying to access a value whose ownership has been transferred somewhere else. Are there other ways we could handle passing this string so that its ownership is not moved to the second function? Yes, and we will cover those in detail in the next video. Before that, let's review these rules of ownership one more time. Each value in Rust has a variable that is called its owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. These rules are how the Rust compiler prevents you from unintentionally creating memory safety bugs in your code. Now that we have an overview of ownership, let's move on to a related concept, borrowing. I'll see you in the next video. Borrowing, like ownership, is one of the most unique concepts of Rust. This video will take you through several examples of borrowing and show you how you can use it to help you write memory-safe code. Let's look back at the code example from the ownership video. As it's written now, this code will throw an error when we try to compile it. This is because when we pass the say string to the printout function, that function took ownership of it. Let's do a quick review of what happens on the stack and the heap when you move ownership of a value. If we create a string variable called say, and then move the value of say to another string variable called say2, the original say variable will be invalidated. What if, instead of moving the value of the say string, we cloned it using Rust's clone method? Then it would copy the value of our first string to an additional location on the heap. And then the new string, say2, on the stack would point to the new location on the heap. Therefore, if we dropped our first string, our second string would still be valid. Let's pass a clone of the say string to the printout function so it takes ownership of the clone of our say string, not the original string. Now, when we run the code with cargo, it runs successfully. Cloning works in some scenarios, but if we don't want to create a full copy on both the stack and the heap, we can use a technique called borrowing. Borrowing a variable creates a reference to the value of that variable. It does not transfer ownership, nor does it make a new copy of the value on the heap. We create a reference to a variable by putting an ampersand in front of it. And in order to pass a reference to a variable to a function, we need to modify the printout function to take a reference to a string rather than a string itself. And now the code works. Instead of passing ownership of our original string to the printout function, we created a reference to the value of the string and passed that reference. This means the main function kept ownership of the original string and we could use it again. In the Rust community, we say the other function borrowed the value of our original string. If you have some experience with Rust and are wondering why I used a reference to a string rather than a string slice, it's because string slices are out of scope for this particular video. If you'd like to learn more about when you would use a reference to a string and when you would use a string slice, check out this section of the Rust language book. This video introduced you to the concepts of cloning and borrowing variables. Tune into the next video for more examples and more information about the rules of borrowing in Rust. Welcome to the second video on borrowing in Rust. When you borrow a variable, you create a reference to that variable's value. References, like variables, are immutable by default. However, also like variables, you can make a reference mutable as well. Let's look at this in action. Here we create a vector with the elements 1, 2, and 3 in it. And then we print the vector out. Next, let's create a function that takes a mutable reference to a vector of 32-bit integers and adds a value to that vector. Back in the main function, let's call add2vec and pass it a mutable reference to my vec. Notice that I need to specify that the reference is mutable when I pass it. And then let's print out the vec again. And when we run this code, we see both the original vector and the mutated vector printed out. The add2vec function was able to take a mutable reference to a vector, then mutate the original vector through that reference. Like with ownership, there are rules for borrowing in Rust. The first is, at any given time, you can have either one mutable reference, as we just saw, or any number of immutable references. The second rule is that references must always be valid. And let's look at an example of this second rule. First, we create a string and assign it to the say variable. Then we assign a reference to that string to the say2 variable. And then let's print out both variables. When we run this, we see the value of both variables printing out just fine. But what if we drop the say variable before we print out say2? When we run the code now, we receive an error. This is because when we drop the say variable here, it is no longer valid after this point, and we cannot access its value. Additionally, any references to say's value, like our say2 variable, also become invalid. One way of referring to the time in which a variable is valid is referring to that variable's lifetime. Say's lifetime starts when it is assigned a value, and it ends when the value is dropped. In order for this code to be valid, say2's lifetime would need to still be in effect when we attempt to print it out. However, because it is a reference to the original say string, its lifetime is tied to the original string's lifetime. As soon as we drop the value of the first string, any reference to that string's value will be pointing to memory that no longer exists. This code errors out because the last line attempts to access a reference to a value in memory that no longer exists. This is another way that Rust prevents dangling pointers. When we compile a Rust program, the Rust compiler runs through a phase called the borrow checker, where it verifies that any values that are borrowed as references are still valid when that reference is used. Before we end, let's revisit the rules of borrowing. At any given time for a given variable, you can have either one mutable reference or any number of immutable references. And references must always be valid. Borrowing is a challenging concept. This is partly because it is such a different way of managing memory than what most programming languages do. Once you understand how it works, however, you also understand what it prevents you from doing and how it makes sure that the code you write is memory safe. I hope this video has helped you understand these concepts, and we will see you in the next one.
Strings in Rust are often one of the first things that trip up newcomers to the language. Unlike most languages, which choose to hide the complexity of string data, Rust does its best to balance ease of use with the reality that strings are not as simple as they may seem. So what are strings all about? Well, first, Rust string type is always valid UTF-8. And unlike in some languages like C, Rust strings are not null byte terminated. Likewise, Rust strings are not simply collections of character values. In fact, there's not just one string type in Rust. Rust actually has multiple string types. Luckily, normal string usage comes down to just two of these types, but keep in mind that Rust has other string types for certain special situations. The first type of string we'll be dealing with is capital S string values. These are known as own strings, which we're illustrating here with a function that takes a string and returns its length. Since these strings own the string data associated with them, they're responsible for freeing the data when it's dropped. This means that when a value of type string goes out of scope and is dropped, their string data is freed. What is a value of type string composed of? Let's take a look at the string contained in the variable s, as well as its associated data that lives on the heap. S is composed of 3 parts. First, it contains a length in bytes, 6 bytes in this case. Next, the string has a capacity, or how much room in memory is reserved for this string to use before we need to allocate even more memory. 8 bytes in this case. If our string grows by 3 more bytes, the string no longer has enough capacity, and the string will automatically allocate more memory. Finally, the string contains a pointer to the data it owns. The string points to the entire data it owns. But what if, for example, we only want to view a particular part of the string memory, like the first line of our string? This is where the second string-related type &str, often pronounced &stir, or called by its longer name, string slice, comes in. This type does not own its data, and the string data is not freed when the value is dropped. This type represents a view or windows, often called a slice, into string data. Let's look at code that finds the first line of the string s. We do this with the lines method. We call next on the return value from lines to get the next line, which in this case is the very first line. And then we call unwrap, which will crash our program if the string contains no lines, something we know is not the case since the string in question s has 2 lines. We store this in a variable called L, which is of type &stir. &stir, unlike capital S string, is composed of only 2 parts, a length and a pointer to the string data. L does not have access to the rest of S's string data. And while we have L, we won't be able to change the data S owns. L is an immutable view into data S owns. Rust guarantees that as long as we can use L, S cannot be dropped. You may have seen that string literals are of type string slice. Now we have tools to talk about why. String literals are embedded directly into the binary executable or library you're building. We can't treat them as capital S strings because we can't own this data. Instead, they are string slices or views into the binary string data section. A common operation in many languages is to get a character at a certain offset in a string, treating the string just like an array. This isn't allowed in Rust, as Rust strings are not arrays of characters. Rust strings are UTF-8 encoded. This means a logical character can be anywhere between 1 byte, as with many ASCII characters, or even 4 bytes big, as with many Chinese characters. In other words, not every byte of string data represents 1 character. Sometimes it represents only part of a character. This is why Rust requires us to be explicit about how we want to access string data, by bytes, by characters, and more. If you're coming from a garbage-collected language, Rust strings might feel confusing. Rust is forcing us to acknowledge the complexity of human writing systems. But don't worry too much. Most of the time you won't need to pay too much attention to this complexity. Let's jump over to a demo to see strings in action. Now that we've learned a little bit about how strings work, let's dive into some code. We'll start by creating a new project and opening it up in VS Code. We'll create a function for getting the first line of any text data. For now, we'll make the argument and the return type capital S strings. The string type comes with a convenient method, lines, which allows us to progressively get each line of the string. We must call next on the return type of the lines function to get the next line. Since this is the first call to next, this gets us the first line of data. When the input string is empty, the call to next returns option none, otherwise returning option sum with the line data. To keep things simple, we'll just call the option type's unwrap method, which crashes the program in the none case. If we try to compile the function as is, we'll get an error. We said our function will return an own string, but apparently the line we're getting back is of type &stir, a string slice. Why is this? It turns out that the line being returned to us is a slice into the string input passed into our function. In other words, it's a direct view into the text data owned by the input string. We're simply being given a view into the original string data. But we've said that the function should return an own string, a string that owns the data associated with it, not a slice into that data. There's many ways to get this code to compile, but like many things in Rust, we need to be explicit about what we want. If we want to keep our function signature as is and return an own string from our function, we need to turn the string slice into an own string. How do we do this? One of the most common ways to do this is by calling toOwned on the string slice. ToOwned turns the non-owned string slice type into its owned equivalent, an owned string. This will copy all of the string data referred to by the string slice and return an owned string that owns the copied string data. What if we don't want to copy the string data, but rather return a string slice to the caller? To do this, we will change the argument and return types to be string slices. Now we're not dealing with owned strings at all. A return string slice points to the same exact memory as the beginning of our input string slice. This means that the input string slice needs to be valid for at least as long as our output string slice. Otherwise, the output string would point to invalid memory. To call our function, we can pass in things that are already of type string slice. Let's create a string slice using a string literal. If we pass this value to our function and print the result to standard out, we should see the first line. Besides passing values of type string slice, we can also pass references to owned string. Let's try that. Now, a reference to an owned string and a string slice are not the same thing. They have different types after all. Rust rarely implicitly converts between types, but this is one case where it does, since it's more or less completely free to convert a reference to an owned string into a string slice. Rust strings come with a whole bunch of helpful methods for manipulating string data. For instance, we can make our string uppercase and strip things from the string. Make sure to check out the Rust standard library docs to see what else you can do with Rust strings. Rust string types can be confusing to newcomers to Rust because they require understanding ownership and borrowing. But once you have an understanding of these concepts, you'll be able to manipulate text data in an incredibly efficient manner. Rust offers a rich variety of collection types that provide a way to store and retrieve data in an efficient and safe manner. Let's explore some of Rust's collection types. Rust collections all have different characteristics when it comes to use and performance. The most common collection type is a vector, which is a growable, continuous stack of items of the same type. For example, a vec of strings is a continuous collection of strings, and as we run our program, we can add and remove items from the vec. Next, there's a hash map, which offers an efficient way to store and retrieve keys and their associated values. For example, we can use a hash map to associate string keys representing people's names and values of type U8 representing their ages. We can then quickly retrieve people's ages based on their names. Next, there is a hash set, which, like a vec, is a collection of items, but the items in a hash set must be unique. Next, a vec dec is like a vec, but always allows for efficiently getting and setting items to the back and front of the collection, unlike vec, which stores new items always at the end. Lastly, there's linked list, which is a doubly linked list. Linked lists are much less often used in Rust than in other languages like C, so I'm only mentioning it for completeness' sake. There are other collections in the Rust standard library. Make sure to check out the docs to learn more about them. So when should you use each of these collections? Vecs are the most common and allow for accessing all the elements efficiently by index. This is usually the default choice when you just need to store items together. Hash maps are best when needing to associate some keys and values. And hash sets are great when you need the extra constraint that all items in the collection must be unique, and you don't need to access items by an index. Vec decs are great for modeling queues, where you want to officially put items to one side of the queue and pop items off the other side. The docs have great explanations of when each collection might be worth using. Let's take a look at how vecs work up close. Here we've constructed a vec of U8s using the vec macro. We see the memory of the heap where this vec's items live. A vec is composed of 3 parts. First, a length, which is 3 in this case. Second, a capacity, which is the amount of room our vec is reserving for its items on the heap. The vec here has reserved space for 4 items. Once the 5th item is pushed onto the vec, it will automatically allocate more memory. Lastly, the vec has a pointer to its data. When dealing with a collection of items that live next to each other in memory, you often deal with a slice. Slices are references to items that live continuously in memory, and we write their type with an ampersand and the type of slices item surrounded by braces. For collection types that store their items directly next to each other in memory, it's trivial to turn them into slices. For example, vec store all their items one after another in memory, so it's easy to turn a vec into a slice. We can turn the vec we created earlier into a slice using indexing notation. Here we're creating a slice that refers to just the first two items of the vec. The slice is composed of two parts, a length, in this case 2, and a data pointer. Remember, slices don't own their data, they just refer to other data owned by some other value. Now that we know the basics of what collections are, let's go ahead and use some of them. Now that we've seen the basics of what Rust has to offer in the form of collections, let's see how to use them in code. We'll start by creating a new library project and opening it up in VS Code. Let's say we're creating an enrollment system for a school. First, we'll create a student struct. We'll give the student one field, name, with type string. We'll annotate our struct with a derive attribute that automatically derives implementations for the partial eq and eq traits. Don't worry about the details of traits and deriving. This simply gives us the ability to test that two structs are equal if their fields are equal. We'll start by creating a vector of students using the vec macro. The macro is shorthand for creating the vector and then pushing each element onto it one at a time. At any time, we can push more elements onto the vec using the push method. We can easily access the students by index using square brackets. Be aware that this attempts to take ownership over the item. This will cause compilation errors since we're not allowed to take ownership over the item, since the student's vec itself has ownership of that item. To get around this, we borrow the item instead of taking ownership by adding an ampersand. Accessing an index that is not present in the vec will compile just fine, but will panic at runtime. If you need to access a specific item in a vec, you may prefer to use the get method, which returns an optional reference to the item. If no item exists at the index provided, none will be returned. Vectors also provided a convenient way to iterate through the contents of the vec by using the iter method, which returns an iterator. Iterators are a whole topic on their own. They provide rich ways of filtering, mapping, and combining data together. Now that we have our list of students, we may wish to store them in a way that allows us to access them by the courses they're enrolled in. For that, we can use a hash map. In order to use the hash map, we need to bring it into scope by adding a use statement. This brings the hash map type into scope for our use. We then can create a hash map and store our students into a class, let's say biology. We do this by creating the hash map and then inserting. This gives a hash map with owned string keys and a vec of student values. If we want to access all the students in a course, we can use the get method just like on vec. This gives us a reference to the vec of students stored in our hash map. It's important to remember that the hash map owns its keys and values, just like a vec owns its elements. This means when we access elements inside these collections, we will only get back references to them. If we need ownership over those items, we need to remove them from the collections, which we can do by using the remove method. Rust collections have many rich APIs associated with them. Check out the Rust documentation for more info.
Let's use Visual Studio Code to see how traits work in action. I'll begin by creating a new project called Traits and opening it up in Visual Studio Code. And inside our main file, let's create a struct called film. A film has a title, a director, and a studio. And now let's create another struct called book. A book has a title, an author, and a publisher. Both films and books come in catalogs. So let's create a catalog trait to contain behavior related to catalogs that can be used on both films and books. And no matter what kind of thing is being cataloged, we need a way to describe it. So let's add a describe method to our catalog trait. And now let's implement the catalog trait for the film struct. When we call describe on a film, it will print out a line that says that the title was directed by the director name through the studio. And in our main function, let's go ahead and create an instance of the film struct. Let's call it Captain Marvel, and it's a film where the title is Captain Marvel, the directors are Anna Boden and Ryan Fleck, and the studio is Marvel Studios. Now let's call the describe method on Captain Marvel. And when I run this code, I see that Captain Marvel was directed by Anna Boden and Ryan Fleck through Marvel Studios. Now let's implement the catalog trait for the book struct. And in this case, when I call describe on a book, it will print out the title was written by the author and published by the publisher defined for that book. So back in my main function, let's create an instance of the book struct and call it Elantris. The title is Elantris, the author is Brandon Sanderson, and the publisher is Tor Books. Now let's call describe on Elantris. And when I run this code, I see Elantris was written by Brandon Sanderson and published by Tor Books. There are a lot of different types of things that can be in a catalog, all of which might have different behavior when you describe them. Let's go ahead and create some default behavior for the describe function in the catalog trait. In this case, when a struct has catalog implemented on it, but does not have its own behavior for the describe method, we will print out we need more information about this type of media. Now let's create a new struct called the album struct. Album has a title, an artist, and a label. And let's go ahead and implement the catalog trait for album, but notice that we do not define behavior for the describe method. We choose to use the default behavior for now at least. Back in my main function, let's go ahead and create an album called Let It Be. And the title is Let It Be, the artist is the Beatles, and the label is Apple. Then let's call the describe method on our Let It Be album. And let's run this code, and I see that we need more information about this type of media. And that is our demo of traits. They can be confusing at first, especially if you're used to object-oriented programming, but as you use them more and more, you see how useful and how powerful they are. Happy coding!
Thank you for completing this beginner series on Rust. We hope that you learned about the foundations of Rust and feel ready to go forward and continue exploring topics we covered in more depth. To further your learning, check out the following resources. First is the GitHub repository for this series. Here we have all of the code demos that were shown in the videos and some extra resources as well. You'll also find some next steps to take your understanding of Rust to the next level. There is also the Microsoft Learning Path, Take Your First Steps with Rust. Many of the topics covered in this video series were also included in the Learning Path, but could be a great place to go next and reinforce what you learned in this series. And if you want to stay up to date with the latest news and updates, make sure to subscribe to This Week in Rust. The most important thing that you can do to continue learning is to get hands-on. We encourage you to write Rust code, whether that's building your own programs or completing exercises. It's crucial to get more comfortable coding in Rust. We also encourage you to become part of the community in a way that's meaningful to you. Feel free to go back and check out Nell's video on the Rust community if you need some more suggestions there. Thanks again for watching. We hope that you enjoyed this series and are excited for you to continue your journey with Rust. Cheers!